right, folks, we're now in topic 5, evolution and biodiversity, and the main goal is for you to be able to understand how the concept of evolution works and how life evolved on Earth. This is split into 4 different subtopics. First is evidence for evolution. How do we even have an idea that happened? What supports it? Remember, when we're always talking about lab reports and IAs, we're talking about where's your evidence? Don't just give me a claim, give me the evidence and why you think it happened that way. So here's the evidence. Next topic is natural selection. What is it? How does it work? Third one is taxonomy. Basically how we name things. You know, nature doesn't really care, but we as humans, we like putting things in different little categories to make it easier for us to understand things. And finally, there is cladistics. How we figure out who's related to who versus the ancestor. You know, you covered pedigrees before and saw, okay, parents, children, next generations, whatnot. This is the same thing, except instead of talking about children, we're talking about species and how life went from, well, you could go from top or bottom, went from one thing and change and change and change until we get what we have today. So when we're talking about evolution, we're talking about, well, change in life over time. Now, you notice I put in the brackets in life. It's change over time is a simplification. Change in life over time itself is a simplification. The definition of evolution that I looked up on the web that you'll find in other dictionaries is the process of cumulative change in the heritable characteristics of a population. Note the word cumulative. That means you're getting not one big change, but multiple changes. So if you hold on a moment, we're going to switch to PowerPoint and illustrate that. All right, so here's a simple example. On the left, we have a dot. On the right, we have a line. When we look at these, we go, okay, they're maybe a little similar. They have colors, the same color, maybe the same height, but how do you get from the left to the right? It's a big jump from a tiny little dot to a long line, right? But what if instead we started with a dot, and we added one, add another, another, until we get the line. We didn't leap from the first point to the next. Instead, we just made small incremental changes and kept those changes until we reach the end point. That is the concept of accumulating changes. Evolution accumulates those changes. Some is lost on the way, but a lot of it is kept and passed on so that we get those improvements or lose ones that won't help us until we reach our final form. All right, here we go. Back to this. Now, when we're talking about evolution, it's evolution of a population, of a species. Yes, an individual might be the one that gets the initial benefits, but unless those benefits are actually passed on to children and those children pass it on to the children, it won't spread throughout the population and you won't have a change. If that individual dies before it has children, those improvements go nowhere. They die. They're gone. Now, who first noticed this, or at least who first wrote it all down and codified it in text and explained it so that more people could understand the concept, were Darwin and Wallace. You mostly hear about Darwin. You heard about him, about his famous trip in the Beagle around the world, and then he wrote eventually The Origin of the Species, that famous book that almost every single biologist, every single biology class that you take in college should force you to read. There's the other guy, Wallace. He's the one who actually caused Darwin to write his book. Darwin had made his observations and he'd been writing it and codifying it, but until he met Wallace, who had reached those same conclusions by himself in his own research, Darwin was sort of procrastinating. You are all pretty much familiar with that. I know I certainly. All right. So if you want to take a look at their story, if you go to www.biointeractive.org or just copy and paste this link, or actually can't copy and paste, type this link out. Biointeractive has made a good short film about the story of the development of the concept of natural selection. One of the first things I think about when I hear the word fossil would be dinosaur bones. However, fossils cover a larger extent than just old bones. It includes anything that is evidence that life has occurred before now. This includes the trilobite fossil that you see on the top right, or plant fossils on the bottom left. If you take a look at a fossil, one that really confused scientists and paleontologists for a long time was basically a sheet of rock with lines all the way down, horizontal lines. This was evidence that there was life, but they could not figure out what made these tracks. Until some time later, they figured out that an ammonite, which is basically looks like a nautilus, except slightly different. They are related. But basically, an ammonite was rolling down an incline, and every time that this lip hit the bottom, it left one of these imprints. Okay, so Earth is roughly 3.5 billion years old. Now, the fossil record shows that life before 500 million years ago was very different from what we see today. For example, the first vertebrates were fish, and they only appeared about 500 million years ago. Then, if you look at the KT boundary, you had the dinosaurs before as apex predators, but after that, well, dinosaurs are gone, so something has to take its place. That's when the mammalian predators first start showing up. The only exception to this great change over time would be sharks, cockroaches, and ferns, and those have been around for a long time. They have fossil record representatives, and us, of course, they are still in existence today. One of the few that survived all that turmoil throughout the eons. Now, fossil record is incomplete, but what it can show us is if you look at the different dates or estimated dates of these fossils and you line them up by time, you can see gradual changes. You can see relationships between the fossils. So even if fossil A at time point A is greatly different from fossil B at time point Z, if you look at the intermediate fossils, you can often detect similarities between the intermediates, even though A and B are completely different. So how do we know where to put those fossils in the timeline? Sure, you can just sort them by shape and just say, okay, this one's close, similar to this one, next one, next one, next one, until we go from A to Z. But how do we know the order that we put it in is correct? How do we know that it actually represents the timeline? One of the ways we do it is through radioisotope analysis. Now, a lot of you have heard of the term carbon dating already, and what that is you're taking a look at a specific radioisotope, carbon-14. Radioisotopes have a half-life, meaning that it's the amount of time to lose half the mass of what you had originally. For example, if you had 1 kilogram of carbon-14, which is quite a lot, by the way, by the end of 5,730 years, which is the half-life of carbon-14, you'll only have half a kilogram. So take a look at the chart on the top right. This is a chart of carbon-14 and its decay rate. If you look at the x-axis, it's age of sample in years. Y-axis, it's a carbon-14 percentage remaining. And if you start off with 100% in 5,730 years, give or take 40 years, you have 50%. Another 5,730 years, you're down to 25%, and then 12.5. So, as you see, every half-life, you're losing half of what's remaining. But once you get to around 5 half-lives, which is 28,650 years, right about here, it gets really hard to determine the difference between the percentage composition of what you have, meaning that you're not sure if the change in percentages is due to actual change in the age of the material or if it's just through experimental error, testing error. So carbon-14 dating is usually only good to about 5 half-lives. After that, it gets difficult to support a difference in age. Now, fortunately for us, there are other radioisotopes that we can use. For example, there's potassium-40, which you find in crystallized magma. Now, this one has a half-life of 1.251 times 10 to the 9 years, which is basically 1.251 billion years. which is gives us a resolution from 100,000 years to about 4.6 billion years ago. Now, if you remember, Earth is only about 3.5 billion years old, so this should be able to help us cover the entire age of the Earth. And the radioactive decay of potassium 50 is on this bottom right chart, just to give you an example, but we usually don't deal with that in biology right now. You might later if you go into more advanced topics, but for right now, just be comfortable with the concept of radioisotopes, half-lives, and mostly what we use is carbon 14.